you all for inviting and attending. I'm going to be giving a kind of extended version of a talk that I've given before at BaseConf. Basically, I've kind of updated the slides to include more details. And it's going to be talking about this algorithm called predictive resampling, which lies at the heart of some of the work that some Bayesians have been quite interested in recently. This kind of predictive Bayes approach, very much building on the work of Dave Finetti and Phil David from like back when this was a big thing. What's really cool is that even though I've never visited BSU myself, I've actually had a lot of ties. So a lot of the work that I've created, for example, this co-author that I've done a lot of the work with, Andrew Yu, is actually a PhD student of BSU. Wan Yue Sun, which is my PhD student now, she was an MPhil student at BSU. And there's another student in my lab who's quite interested in actually joining your department as well. So I've heard many good things about your department. So it's a pleasure to be here today. So kind of in a nutshell, then my talk is basically going to be at this interface of prediction and inference. It's going to make this interface very explicit. Usually you see the direction of inference leading to good predictions. This time it's going to be kind of the other way around. So you can actually use prediction to carry out Bayesian inference, and you get this quite interesting algorithm that comes out as a result. So I'm going to start with an introduction of this framework. If you've seen some of my previous talks before, this might be a little bit boring. But section 2, we're going to go through a lot of different examples that some of which have been developed more recently, which try to extend the framework and push the boundaries of what we can actually tease out of this algorithm. And then in section 3, I'm going to talk a little bit about some of the convergence properties, so a little bit more kind of practical, especially for those who work in Bayesian computation like MCMC and diagnosing samplers. You might find this part quite interesting because the algorithm itself is very different to the regular kind of Bayesian computation that you have. So predictive Bayes in a nutshell, which kind of lies beyond this algorithm, is using the posterior predictive density directly as your model. So we're actually going to start with the predictive density as our model instead of the regular likelihood and prior kind of elicitation. And in a nutshell, then basically the way that we access the posterior is through this sequence of predictive densities. So you can construct a joint predictive density, which I'm going to show you how to do shortly in an algorithmic way, which is basically a sequential imputation step. And by constructing this joint predictive density and computing parameters as functionals of this population in a very bootstrap-like way, you can actually kind of get a posterior distribution out of this. So this talk is going to talk a little bit more about the practical side, because I find that to be quite interesting to explain, which is that if I were to explicitly choose a model like this, which I'll introduce in more detail shortly, how do I actually get access to this posterior distribution? And are there computational advantages over traditional Bayes? So that's kind of one of the main reasons why I'm interested in working in this field, for the potential computational advantages. So we're going to introduce this algorithm called predictive resampling. Underlying it is actually a lot of kind of beautiful theory that's been developed over the years, and a lot of philosophy as well around statistical modeling through prediction. But today I'm mostly going to focus on how you can actually get a posterior, in particular without an MCMC sampler that is basically asymptotically exact. So why would we want to do this, and why there's kind of been a resurgence recently? Well, we've actually gotten quite good at eliciting predictive densities. So this is kind of the enthralling part of the methodology that got me really hooked, was that there's this promise of constructing really accurate predictive densities with machine learning. We're going to see that there's a little bit of a caveat when it comes to this framework for this part shortly. One statement that I think is a little bit underappreciated as well is that it's very easy to make statements about data. So I think this was kind of what some of the early proponents of predictive Bayes argued. But for observations, which are actually observed, it's quite easy to evaluate. So you can tell by just looking at data whether or not your predictive distribution is good. It's quite difficult to do that with a prior because you never really see your parameters of interest. And finally, and probably the most important part, at least for this talk, is that sometimes the computation required for posterior inference can be much more expedient. In fact, the computation is so different that it's quite hard to compare sometimes. When you implement it in practice, it's like orders of magnitude faster. So approaching speeds of things like variational Bayes, but still being exact. So the kind of philosophy behind this method is that instead of accessing the parameter directly, we're going to work with data points. So I guess you can argue that when you observe a finite sample y1 to n, you actually just want to see the rest of the population. And we're going to kind of take that very literally in this framework. So we're going to argue that if you had access to this infinite population, maybe through sampling or just the empirical distribution, then you could actually compute any parameter that you'd want to know course, assuming that it's a measurable function. So in some of the work that we've been working on recently, we argue that actually you can motivate posterior uncertainty as being the push forward of predictive uncertainty. So this kind of population that you haven't seen yet, yn plus 1 to infinity, is the driver behind all the uncertainty that you see in Bayes. And what this translates to is an algorithm that's quite bootstrap-like, which is, I guess, really interesting. So the idea is that you can actually prove, at least for parametric models under some assumptions, that if you were to carry out an algorithm like this, where instead of resampling data that you've seen before, you're going to kind of resample this future population that you haven't seen yet. And you need to access this using the joint predictive density, say the one that comes from your Bayesian model. If you then compute a kind of bootstrap-like estimate, so you draw an imputation of this population, you compute your parameter of interest, like a bootstrap, you can prove that the uncertainty in this theta infinity, right, driven by this uncertainty in the missing population, is exactly coming from the posterior distribution that's kind of lurking underneath this joint predictive density. So when you write it down like this two-liner equation, the posterior doesn't actually show up anywhere. So you can argue that the Bayesian directly imputes what he needs or they need to calculate whatever parameter you want. And you can formalize this using Dup's theorem, which are based heavily on martingale arguments, which is also the namesake for the method that we'll see shortly. So in a nutshell, you can view Bayesian inference in this other lens, which is actually a little bit closer to the frequentist lens because it's working with data. But instead of data that you've seen, you're going to be looking at data you haven't seen yet. And this is very much restricted to the IID setting for now. We're going to talk a little bit about that at the end. So how do I actually do this kind of messy step in the middle? And that's going to be the focus of today's talk, this crazy big looking joint predictive. And well, we can actually break it down into a sequence of one step ahead predictive densities, which is much easier to work with and much more kind of palatable in this machine learning world where you're usually predicting one data point at a time. So we're going to denote this predictive density pi, p subscript I, as the predictive density for a new datum given the history. So you would basically start at Pn if you were to see n data points. And what we're going to do is we're going to factorize out this joint density that I was talking about earlier into a sequence of one step ahead. So this is simply the chain rule. Like here I just have basically the big joint density broken up into little one step ahead predictive. So nothing special, mathematically true. But what this actually implies is a kind of sequential imputation algorithm that lets you have access to this big joint if you specify the sequence of predictive densities. So I'm going to run through an example later, so don't worry if this is a bit abstract for now. The main part that I want you to focus on is this inner loop here. So the outer loop is just the number of posterior samples. And the inner loop here is basically going to be running through from n plus 1 to some large-ish integer capital N, where you're going to repeat the step of sampling from your predictive distribution and then treating that random datum, yn plus 1 or yi in this case, as if it was actually observed from the population. So you're going to update your predictive distribution with this fake data point. And if you do this onwards to capital N, you can show that this is the same thing as drawing from a joint sample, from this joint predictive that's implied by the sequence of one step aheads. And I guess the thing that's really interesting is that this step here, this updating step, is kind of where all the magic happens. So we're going to spend some time going through some examples of this. But if you run this onwards to infinity, you can actually recover some kind of Bayesian uncertainty in this parameter of interest. So I'm going to show you that on the next slide for a very popular example. Of course, one thing that you might already spot is that computation grows with capital N. So this is the number of posterior samples on the outside, but you have an inner loop that grows with capital N. So this looks pretty expensive, actually. It's a bit surprising that this can be faster than MCMC. So we're actually going to talk a little bit about why this might be the case, as well as some interesting approximation schemes that are, again, asymptotically exact. Also, in practice, even though the inner loop is big, you can design models so that the step is very fast, and you still get computational gains of over like orders of magnitude. Okay, so an example, we're going to basically break down this algorithm into these two steps, the imputation step and the update step, and we're going to look at what happens, right? What does this trajectory look like? What do these imputed samples look like? The example we're going to use is going to be an actual Bayesian model, because so far we haven't actually moved away from it yet. We've just assumed everything kind of follows out of the Bayesian model. So if you stick to a conjugate Bayesian model where you have this likelihood and prior that's conjugate, it's not too hard to show that your posterior distribution is also going to be Gaussian. But we're going to actually start the other way. We're going to start with the posterior predictive density, which you can calculate directly, right? So in this case, you're going to be having a normal density with some regularized version of the sample mean and your sample variance plus some posterior variance. And the imputation step is going to be really straightforward. You just draw a random variable from this Gaussian. So you're going to estimate this from some data set, and then you're going to draw the first Gaussian at random from this predictive distribution. The update step is also quite easy, right? It's very easy to see how the data comes into this estimate. So you're just going to update the sample mean by treating this new random datum as a real data point. So you're going to estimate the sample mean here. Then you're also going to update the sample variance, taking into account that you observed one point. And what you can do is then you can run this onto capital N, and that gives you one trajectory, one imputed population, one sample from the posterior. So what does this look like in practice? Well, we had this little simulation that was in the original paper where we generated some data, like some IID data, because you need to start somewhere. Like you're not going to make all of the data up. You want your kind of data set still to be real, which is going to start from the sample mean of 1.84. And each of these gray curves that you can see here are basically going to be tracking the estimate of theta bar n, so the mean, basically. You're going to be tracking the population mean as you impute more and more of the population. So initially, there's a lot of kind of wiggling in variance because there's a lot of noise, right? Here, you're going to be drawing Gaussians, and they're going to have very heavy weighting in this sample mean. So you just get this kind of wiggling about. But as you impute more and more of the population, it stabilizes to a value. So each of these lines kind of stabilize. What's really happening under the hood is actually a kind of martingale convergence, which we'll talk about briefly later on. But the kind of heuristic or intuition behind this is that you're imputing more and more of the population. So you're kind of stabilizing to a global estimate. Your estimate is kind of consistent. We know that the sample mean is consistent. The only difference is that each of these trajectories actually converges to a slightly different point, right? Because you're getting a different population for each trajectory, this kind of infinite population, which then gives you a mean. The mean is going to be slightly different across the populations. And the equivalent result that I mentioned earlier for dupes is that if you look at the distribution of where these trajectories end up, you just plot a histogram of where all of these end, and you overlay it on top of the posterior density, which we know is Gaussian with this mean and this variance, then they actually overlap. In fact, they're exactly the same. You can prove mathematically that this converges almost surely to a sample from this distribution. So what we've done here is we've taken an algorithm that relies only on a predictive density. We've kind of done this interesting predictive resampling algorithm. It's kind of like a recursive bootstrap in a sense. We've looked at the parameter of interest as a function of the population at the end, and we've recovered the posterior. But nowhere in that process did I actually need to do any kind of accessing the posterior. I didn't even need to talk about it. The predictive density could have actually come from nowhere. Indeed, that's going to be the very natural next step. We're going to basically keep all of these aspects of the model, but we're going to relax what this predictive density can be. So this is a framework that has a couple of names. It's mostly called predictive Bayes because that's the way you worked with it. But in a paper that I did during my PhD, we coined this term the martingale posterior because there's this kind of very nice martingale condition underlying it. So I'm going to mention that briefly later on. The idea here is that you can generalize Bayes. So instead of being stuck with the posterior predictive density that's implied by your likelihood in your prior, maybe you don't want to choose a prior, maybe the computation is too difficult. You can actually just construct your model directly as a sequence of predictive densities. And the rest of the talk is going to go through many different examples of this, so don't worry for now. And actually, this is still a pretty open question about how general this is. And you're also going to have some parameter of interest, which we're just going to leave abstract for now. I'll give you some examples of kind of traditional functionals that come out in robust statistics. And what's interesting about this framework is that throughout the whole process, I didn't need to specify likelihood in a prior, not even the prior, which is kind of remarkable. But the predictives in this case need to satisfy a kind of martingale condition. And actually, it's quite a deep condition because underneath it, there is a kind of hidden Bayesian model, which I'm going to briefly talk about on the next slide. But if I were able to construct this kind of model and I could specify my parameter in this kind of functional form, then accessing the posterior is exactly the same as that algorithm I outlined earlier. So you sequentially impute, this time from a sequence of predictives that you choose independent of the Bayesian model. And then you compute your parameter of interest very much like a bootstrap. And what we called in this paper is this distribution of theta infinity, the limit, is going to be called the martingale posterior. So the Bayesian posterior, of course, is a special case, but there are quite a few interesting algorithms that don't lie within the Bayesian model, that lie within the martingale posterior. Before moving to the kind of more practical and interesting parts of the talk, I do need to pause for a second to talk about this martingale condition. So it is the namesake. It wasn't my decision. It was actually my supervisors who really loved this martingale name. So the martingale condition so far is the one tool that kind of keeps us tied to Bayes. It's not the most relaxed. You can actually relax it further. But the main idea is that you can't just choose any predictive sequence that you want. So it needs to satisfy this very specific equation here, which is that if I were to impute a sample for my predictive density, and then I updated it, on average, my update should be unbiased. So what this means is that you're not introducing any new bias when you're trying to do this predictive resampling algorithm. The intuition is there's different ways to attack it. One way to attack it is in terms of coherence. You can argue that at time n, you've seen all the real data. So any kind of simulations that you do should be unbiased with respect to that. You're just making up data, right? You're just teasing out uncertainty. There's no kind of estimative information in there. All you have is this uncertainty quantification. So by enforcing this kind of unbiased condition, you can show that when you do this predictive resampling algorithm, all you're getting is uncertainty, but you're not changing the actual point estimate. So the mean, for example, there's no new information being added. There are other reasons as well for keeping this martingale condition. One of them is mostly technical, but there's also a kind of elegant Bayesian interpretation of this in terms of coherence, right? You want your predictive sequence to mesh together. Otherwise, you're just basically not really a statistician anymore. So underlying this martingale condition is this really nice theory by some Italian probabilists, Berti and Rigo particularly, which is called the conditionally identically distributed sequence. There's some really nice theory. You can prove that it is really a weakening of exchangeability and like kind of weakening it just enough that all the things that you want for Bayesian inference, such as the existence of this martingale posterior, is enough. And recent work, I've actually been able to relax this martingale condition or at least tweak it to make it more amenable to different settings. We're also going to talk about that shortly. But the main gist of this slide is you can't just choose whatever model you want, but we're getting closer and closer to making it more general. In terms of the parameter of interest, actually, this is more vanilla. So you can basically choose whatever parameter you want as long as it's kind of nicely behaved. So one way to write this, for example, is the minimization of some expected loss function. This is a very popular approach. Basically, for a given distribution, F0, you can calculate some functional. For example, something like this gives the median, the absolute value gives the median, the squared error gives you the mean. This is a very canonical, robust statistics setup. The interesting one actually that is quite popular these days as well is to use a parametric model, so you target the KL minimizing parameter as your parameter of interest. And you can still kind of reason about uncertainty in this non-parametric manner for a parametric parameter. And actually, this functional goes beyond forms like this. We've managed to get things to work for like densities, quantile functions, things that are not smooth. All of it is hard work, but it is possible. So in a nutshell, then basically, the martingale posterior just consists of two steps. You need to choose your sequence of predictives, and you need to carry out this algorithm. And to do this algorithm in practice, you can't take things to infinity, so all of those limits are kind of inaccessible, which is why I mentioned earlier that computation is still asymptotically exact. But it turns out this truncation is pretty harmless. We're going to go through a little bit of some examples about why that's the case later on. So when you choose your model now, then we're basically going to be restricted now only to specifying this sequence of predictive densities. This sequence of one-step ahead predictives, which are kind of easy to work with because they're just basically density estimators. You can think of this as your best guess of the sampling density. And I'm now going to go through basically many different examples just to give you some flavor as to how the field is kind of meshing together, and then talk a little bit about the computation at the end. So it's clear, for example, that if I chose the posterior predictive density as this P of yn plus 1, Dup's theorem gives that this is exactly equivalent to sampling from the underlying Bayesian posterior that it used to construct this predictive. The one kind of motivator, and probably my favorite algorithm of all time, is when you choose this predictive distribution to be the empirical distribution. So if you choose this distribution to be the empirical distribution, you can show that you actually recover something called the Bayesian bootstrap, which we're going to show you a little bit of later on. There's actually deeper ties because the empirical distribution kind of is related to the frequentist bootstrap when you view things in this way. And it really, at least in my opinion, sells the point on where the difference between Bayes and frequentism really is. And interestingly, at least in our opinion, it's not really the prior, it's more about the kind of population. The one thing that, of course, is most interesting is methods that lie outside these two classes, because the Bayesian bootstrap is still kind of Bayesian. You can prove it's still exchangeable. And these are methods that have some kind of martingale property, and there are different versions of this, which I'm going to run through now. And they're all kind of loosely in this class of martingale posteriors or predictive Bayes. So one example we're going to do is we're going to use this bivariate copula update, but we're also going to go through a few more examples. So this is going to be the second part of the talk now. I've kind of given the motivation and the theoretical quantity. We're not really going to need that martingale condition anymore. We're just going to briefly mention it. But now I'm going to run through quite a few different examples of predictive distributions that you can use. And they're kind of differing in levels of complexity. You start with some easy ones, and you can get to some pretty complicated non-parametric ones. And loosely speaking, there's a kind of divide between the parametric and the non-parametric case. In some sense, the parametric is a little bit less interesting, but a lot more tractable, so we can do things like theoretical proofs. The non-parametric one is probably more interesting for general practitioners, but again, there are still kind of difficulties with this, but I'll give you some examples shortly. So we're going to start with the most simple, which is basically an extension of that Gaussian example that I gave you earlier, right? We had this predictive distribution that was Gaussian, and we had kind of fine control over the parameters of interest. We just updated the mean and the variance, basically. Very easy. So one kind of direction, which has been quite popular recently, is to use the plug-in parametric predictive density. So this is the frequentist plug-in density, and then to update your predictive distribution using stochastic gradient descent. And it's weird because what you end up doing is you end up using a plug-in predictive to get a posterior distribution, and you still get the posterior. So it kind of highlights that you don't really need to do this mixing over the posterior density. That's not really where the uncertainty is coming from. So the algorithm is very simple. It's just kind of your vanilla stochastic gradient descent, right? You take your parameter of interest, you see a new data point, and you add some scaled version of the score function to it. So very vanilla. The scale is actually very important. I've simplified things here. The only difference to regular stochastic gradient descent is that you're not using real data. Instead, you're using data that's imputed from your model, and specifically is going to be imputed from the model at your previous time step with theta n plugged in. So very much like this kind of sequential imputation algorithm. So here then, your plug-in predictive is actually going to directly replace your posterior predictive. You can view this as a prior-free approximation if you'd like. Basically, instead of integrating the likelihood, I'm just going to plug in an estimate. But this update step here is what gives you the kind of dependence between the predictives that then gives you this posterior uncertainty that you kind of want. So interestingly, in the parametric setting, you have a different martingale now because you know that the score function is drawn, sorry, the yn+1 is drawn from the same density. We know that the expectation of the score function for a well-specified model is always equal to 0. And in this case, you're simulating from the model, so it better damn well be well-specified. And it ends up being that the martingale is actually your parameter of interest, which is not quite the same thing as this CID property I mentioned earlier, but basically all of the properties that you really need follow directly from that. So this method is interesting because it lets you do prior-free parametric inference, like really prior-free. So I can, for example, come up with posterior distributions that have the MLE as the posterior mean, even for weird parameters like the variance or like skewness terms, which are kind of canonically quite difficult to put improper priors on. And of course, it's a little bit of a toy example because these are just simple IID parametric models. So I'm actually actively working on extending this idea to the high-dimensional setting when you actually have sparsity information, and it turns out to be much less trivial than we anticipated. It's actually quite a non-trivial extension where things get a little bit complicated because of your parameter not being identifiable. So I'm working on this with actually an alumnus of BSU. She was an MPhil student and now a PhD student with me. So just an example from one of our recent preprints as to the kind of speedups that you can get. There is a lot more machinery that goes on here, which I'm going to talk about at the end. But just for a student t-regression example that's moderately sized, it's not the most difficult problem, but it took MCMC about 2 minutes on my MacBook Pro. So reasonable amounts of time. It was mixing really well as well. So if I were to do this predictive resampling algorithm, and I'm careful about how I do the truncation, like we're going to talk about that shortly, you can speed things up to be about 14 seconds for predictive resampling without any parallelization. So actually, this comparison is a little bit unfair for us because we are relying on basically, we have a parallelizable algorithm that we're still doing sequentially for predictive resampling just to get things kind of on the same page. But what's really crazy is that there are asymptotic approximations, which are extremely accurate. You can actually prove theory about it. And you can get speedups up to this, so 0.03 seconds. And just to look at the posterior distributions, they look almost the same. Right, they're just kind of the black dot. Sorry, the solid line is Bayes. The dotted line here is this approximate predictive resampling idea. So you get a speed up of this kind of ridiculous amount. And actually, in the non-parametric setting, is also pretty crazy. Just because MCMC can really struggle sometimes. We're also going to talk a little bit more about how computation is quite different because the predictive resampling is kind of like a bootstrap. So you get samples that are independent, and the kind of convergence issues that you struggle with are very different to those of MCMC. So it makes things a little bit hard to compare, but I think, at least for me, it was convincing enough that I could do something in like a ridiculously small fraction of time. So this gave me a little bit of hope for really speeding things up for Bayes. Just before I move on to a more interesting example, I just need to briefly talk about the Bayesian bootstrap. It's going to be relevant for the next slide. The Bayesian bootstrap we're going to start with because it's the most simple non-parametric predictive distribution. So earlier we had the kind of obvious plugin one. Here we kind of have the obvious non-parametric plugin. We're going to use the empirical distribution as our predictive distribution. So this is just going to be choosing the n data points that I've already seen as the predictive distribution that I'm going to start with for predictive resampling. And in this case, predictive resampling is also quite nice. Drawing samples from the empirical distribution means you pick one at random with weight 1/n, super easy. Updating it as well is quite easy. You just basically double one of the data points, right? Whichever one you picked, you reweight it by this extra weight. And because all the data points that you're drawing are always going to be coming from the support of the empirical distribution, you can prove that when you do this to infinity, you basically recover a version of the bootstrap. You basically get this reweighted empirical distribution where the weights are going to come from the Dirichlet distribution. But this kind of illustration is neat because it shows that the martingale posterior does recover something that's quite friendly and familiar, which is the Bayesian bootstrap of Rubin and kind of all these connections to the Dirichlet process. So this algorithm itself is actually quite popular on its own for uncertainty quantification because it's really fast as well. And you basically just have to reweight your data and compute the functional. So some recent work that I've been doing basically combines these two. We look at the empirical distribution as having this nice non-parametric property, but the predictive distribution that's parametric has this nice regularization property. And what you can do is you can actually construct this semi-parametric predictive distribution, which merges the previous ideas. It's a simple equation to write down, but actually some of the theory is quite technical, which was driven by my MPhil student, Edwin here, who's also interested in joining your department, actually. So the idea here is that for the predictive distribution, you're now going to have a weighted sum of a parametric component and the empirical distribution. And this is going to be very much just the plugin distribution. So the same kind of parametric distribution that we're interested in with a parameter you're going to update. And C is kind of the weighting term between this parametric and non-parametric component. And obviously, as you see more and more data, the non-parametric component will dominate. So what this lets you do actually is it lets you basically work with the semi-parametric predictive distribution. You kind of get the best of both worlds. You get this regularization towards a parametric model, but also you get this nice asymptotic properties that come nicely with the Bayesian bootstrap, especially when your model is misspecified. I like to view this more as a regularizer for the empirical distribution. The theory behind this is quite tricky. It's not so easy to actually construct a martingale in this setting, but we managed to come up with something that's relatively intuitive. So you're working with a mixture, right? So there's a parametric and a non-parametric component. The parametric component, clearly your parameter is the thing that you should be kind of keeping unbiased with respect to. In the non-parametric case, the actual predictive distribution is what you'd be unbiased with respect to. So when you're working in a semi-parametric case, the moments are kind of a nice in-between. They're not quite parametric, but they're also not like the scale of full non-parametric CDFs. So what we ended up doing was we managed to construct a method that preserved the moments of the underlying predictive distribution to be a martingale. In this case, the number of moments that are required to identify theta n. And actually, if you develop the theory further, you actually get the full picture. So this method of moments idea is actually general enough to cover any kind of non-parametric and parametric mixture. You can prove all kinds of convergence properties. There's also this interesting kind of choosing of C between these two using a frequential scoring kind of argument. Again, lying very much in this predictive approach. So this term frequential just means predictive sequential, which was coined by Phil David. So this model is interesting. I mean, it's actually really just a special case of the mixtures of Dirichlet processes. But what you end up being able to show at least is that you're not stuck with just parametric or non-parametric. There is a vehicle for which you can move along with this. And again, this computation is quite fast. I'm now going to dedicate the rest of the talk actually to more non-parametric examples. Actually, this is probably where there's real practical advantages of the martingale posterior. We're going to look at some examples based on densities and quantiles, which I've been working on recently, and have some kind of fun math underlying it, but also the kind of applications and computation are quite interesting. So in this first example, which was kind of the main example driving the martingale posterior in its original work, is a Bayesian version of the kernel density estimate. So I'm sure that many of you might have heard of these kind of Bayesian mixture models before. Maybe you've heard of a Dirichlet process mixture model. So these are Bayesian versions of kernel density estimation that require clustering, but they all kind of require this very heavy Markov chain Monte Carlo sound, especially because your parameters are discrete. So you get some really kind of nasty stuff. So what we came up with, borrowing on some work from previous people who've worked on predictive distributions, is to actually construct a kind of recursive version of the kernel density estimate. So here I have an update rule. Instead of kind of directly specifying the predictive, I'm going to specify my new predictive as a function of my old predictive and this new datum that I've just seen. And what we're going to do is we're just going to do a weighted sum of my old predictive with this kernel. So I'm just going to leave this undefined for this talk. You can take a look at the paper if you're interested. And it's a kernel that's constructed using a copula. And notice the index I, which indicates this guy is actually adaptive. It's going to change with the data points. So just to see what this looks like, so it's not like kind of voodoo magic, the copula kernel is very much like a regular Gaussian kernel. So on the plot on the left, we have the previous predictive distribution here. The black dot is the new datum that I'm going to update, and then these solid lines are just this copula kernel that's been plotted. So it's clearly kind of centered at the data point of interest, and as I decrease the bandwidth, it becomes less and less peaked, just like a regular kind of Gaussian kernel. You do notice, however, that when I decrease the bandwidth, which is just a scalar that controls how peaked it is, you actually move a little bit away from the data point and closer to this dashed line here. So this is the part that's quite different to regular kernels. When you decrease the bandwidth, you actually get regularization towards your previous predictive. And this is an adaptive property, actually. So you're learning your kernel from your predictive distribution. And actually, this is exactly what you need to have the martingale condition. But you don't really notice this in practice. So when you take a weighted sum, this kind of weighted sum here, then your new density is clearly the old density plus this blob at your new data point, very much like a kernel density estimate, but the kind of peakness of the blob is going to depend on your bandwidth. So you choose a smaller bandwidth, you get something more peaked. You choose a bigger bandwidth, you get something more broad. So a very intuitive algorithm. This part is less intuitive, but I can assure you that it basically just looks like a kind of Gaussian kernel with some terms that are a little bit funky and depend on previous data points. Very easy to compute though. So what you can do is you can use this as your predictive Bayesian algorithm. You can use this as the vehicle for predictive resampling. Very easy to draw a data point from this Y. I'm not going to kind of promise you why, but there are ways to do this in a very easy way. You just update using this kind of very intuitive kernel copula update. And what you end up getting is posterior plots for the density, because that's kind of the parameter of interest in this case. I'm looking at the posterior distribution over my actual density function. So on the figure on the left here, you have this copula kernel idea. So I'm just basically doing the predictive resampling algorithm with this online kernel KDE. It looks like this. And you don't actually need to do any funky Monte Carlo. There's this like really nice trick where it ends up just being uniform random variables. So I can show you a little bit of that later on. On the right-hand side, you have the regular Dirichlet process mixture model. You can just think of this as like a Gaussian mixture with many, many components. And you can see that they're pretty much comparable. The black line is the posterior mean. The gray lines are the pointwise 95% credible intervals. And yeah, there's a little bit of difference here. There's more uncertainty here and less uncertainty here. But they're both reasonable descriptions of the density and reasonable credible intervals. What's interesting, however, is that even without parallelization and without proper optimization, the method on the right took about 2.5 seconds. The method on the left took about 2.5 seconds. The method on the right took about 25 seconds. And this is without any kind of the new theory that we developed recently. And so this is already a 10 times speed up without much effort at all. And actually, we can also recover kind of equal size gains, perhaps even more noticeable gains when you increase the dimensionality, because we know MCMC is pretty poorly behaved for mixture models, especially in high dimensions. Some recent work that I've been looking at is actually to solve another similar problem, which is to do quantile inference, in this case, nonparametric quantile inference. We basically borrowed a similar idea. So instead of updating the density, we're going to update this kind of smooth quantile function with this recursive update. It looks a little bit like stochastic gradient descent, but instead of adding a kind of spike, you're going to add this smooth quantile. So you can kind of view this term on the right as a kernel that's centered roughly at this new data point that you observe. And this quantile kernel looks like this usually. Basically, you add a kind of dip at where the data point is less than your quantile, or you add a kind of bump otherwise. And then you can smooth those out using a similar kind of bandwidth idea. So here you're like totally outside Bayes, right? Like at least in the previous example, there was clear close connections to Dirichlet process mixture models. Actually, this is where the copula comes from, a Dirichlet process mixture model. But here you're just completely outside of Bayes. Like there is no Bayesian likelihood and prior that recovers an update like this. It's just something that's kind of intuitive. In fact, it's actually just a variant of a frequentist model that we came up with, It's basically a smooth version of stochastic gradient descent for the quantile function. What's neat as well is that there's this kind of nice interpretation here, which is that the quantile function, unlike the predictive density, can be viewed as a generative model. So you know that if you draw a uniform random variable and you compute the quantile function of that random variable, that's going to be drawing a sample from Pn, which is implied by this Q. So we've come up with basically a predictive resampling scheme where you don't even keep track of the predictive anymore. You keep track of the sampler, essentially. So kind of closer to these generative AI things. It was a little bit of hype to use this word, but whatever sells the paper, I guess. So here in this case, actually, though, you really do actually draw samples in this way. You draw uniform random variables, you plug them into your quantile estimate, and you get an output that is distributed according to this implicit Pn. So just like the copular methods here, sampling is extremely fast. It's much faster than MCMC. And you can get kind of uncertainty plots that look very much like Bayesian uncertainty. So here's an example of posterior uncertainty on a quantile function, which decreases as you see more and more observations. And you can also compute functionals. So for example, you can look at the mean, which is just a function of the quantile function. Again, you get this kind of posterior concentration. Of course, the main thing that I want to sell is that actually when you do this, you can extend it to the quantile regression setting, and you do get pretty ridiculous speedups as well. So in this specific example, I'm going to show you later on that there's another nice asymptotic approximation in this setting, which is somewhat unique to the quantile setting. We compared this to the state-of-the-art dependent quantile pyramid, which is the most recent work that looked at constructing nonparametric versions of quantile regression, and you get pretty similar results. So uncertainty is a little bit broader in the middle areas and a bit smaller in the tails, but your posterior distribution over kind of regression coefficients look very similar. But the main thing we want to highlight here is that we took about 30 seconds for exact sampling and 1 second for this approximate sampling, which I'm going to introduce in the last 10 minutes of the talk. Whereas this kind of optimized version of MCMC put into C++ took around 26 minutes. So I looked through the implementation, it's really efficient. There's just no way around it. You have to sample all these latent variables. It's just a difficult algorithm. But here we are basically getting negligible amounts of time. In fact, actually the 1 second is mostly spent doing hyperparameter tuning because the sampling itself is very, very quick. And we're going to talk about how we actually do this approximation shortly. It's not even really an approximation. It's more like an asymptotic guess. It's an asymptotic result, basically. So we're going to show you how to do this shortly. So again, pretty insane speedups, but there are some kind of caveats that this only really holds for simple models like this. Okay, so for the last 10 minutes, I'm just going to talk about a little bit about things I've alluded to, things like convergence, this kind of approximation idea, just to illustrate that the computation itself is very, very different. And you can actually find a lot of ways to make things even faster without too much effort. And we're going to talk a little bit about how the convergence is quite different to MCMC. In a sense, it's a little bit easier to diagnose problems. And you don't really have problems with the sampler. It's mostly just waiting for it to finish running. So a very kind of obvious open question is that how large should I truncate before I kind of stop this predictive resampling algorithm? We saw earlier that you can't run things to infinity, but you actually want to access this thing at infinity. How much is enough? So the first thing to note is that you can show using the martingale arguments relatively easily that every time you truncate later, you actually get closer and closer to the sample. So you get this almost sure convergence, which means that you don't need to worry about like ever kind of drifting off. Like you're always going to converge. It's just a matter of waiting long enough. So one thing you can do, which is what we started off doing in this martingale posterior idea, was to monitor these jellyfish plots, is what we call them, these trajectories of your parameter of interest. So in the non-parametric case, you can't keep a trajectory of like a whole function. You need to summarize it. So one thing you can keep track of, for example, is like how far you've moved from the initial estimate in like some distance. In this case, we use L2 distance, which has nice properties. So you can see that even for the quantile function, after like say 10,000 iterations, like you're not moving at all. Actually, after 6,000, you're not really moving that much anymore. So you can use this to diagnose basically convergence, right? Because these flat lines indicate that the quantile estimate has converged. And it will always converge at some point because it's constructed to be a martingale. So if you want to kind of really dig down and like quantify when to truncate, then you can do arguments based on concentration inequalities. But recently we found an approach that's a lot more satisfying, which is to not actually kind of do this hard truncation. Another thing I wanted to highlight is that when you truncate early, you tend to get posterior distributions that are just like a little bit too tight. So this is the yellow line here. You can see the uncertainty when I truncate at 100 instead of 5,000 is quite noticeably tighter than the other examples. But when I reach 5,000, it's pretty much kind of negligible, the difference up until 10,000. So maybe 5,000 is a good place to stop if I were to do this kind of vanilla predictive resampling algorithm. But what's really neat is that because you have all this really elegant and beautiful martingale theory, you know that your sequence you've constructed is a martingale. You can actually leverage that to your advantage. So that's kind of recent technique that was developed by, well, the theory was developed by works of Sonia Petroni and Sandra Fortini. It's like really beautiful theory. And then we applied it in our setting. So what we're going to use is actually a martingale central limit theorem, which means that you can actually show that this kind of remaining uncertainty is going to be Gaussian. So I'm going to show you what this looks like on the next slide. This was formally introduced by Fortini and Petroni in the context of another algorithm. So by constructing these central limit theorems, you can basically approximate this truncation step with a Gaussian. So you can truncate and finish off the sampling with Gaussian, which is quite an interesting kind of property here. So the main idea behind truncating is that you basically want your truncated theta n, this trajectory that you stop, you want the distribution of theta n to be close to theta infinity, like in distribution, right? So basically you want this kind of yellow curve to be closer to this blue or green curve. So what you can actually do is you can actually directly study the difference between this theta infinity and this theta n. You can actually directly study the tail that you've lost because you've truncated it. And it turns out that because things are martingales, you get these nice central limit theorems that follow very naturally. And actually, you can show pretty easily that the remaining kind of noise that is missing from the truncation, like notice here that it's too narrow, right? So there's some noise that's missing. The remaining noise is actually Gaussian with this kind of random variance. So this is a funky term that shows up from the martingale. So actually, to illustrate what this looks like in practice, I'm just going to show you what this diagram is. Basically, the idea behind using this kind of central limit theorem is that when I carry out predictive resampling, I need to truncate at some point, right? So let's say I pick this point 800. And what I want to know is, what is the difference between this theta that I chopped off here and this theta all the way out at infinity, right? So how much kind of noise have I been missing, right, by this early truncation? And it turns out that you can quantify that noise. That noise has a specific mean, which is 0. And the variance of that noise is also something that we can estimate. So you can come up with this algorithm where basically you carry out predictive resampling until your computational budget, you stop, you know you truncated too early, and you're going to add some noise at the end to finish off predictive resampling essentially. And because of all these central limit theorems, we know that this extra noise that you should add asymptotically should be Gaussian. It just needs to be scaled by this variance term. The variance term is also random, which is interesting and different to kind of traditional Monte Carlo things that you estimate. So here's an example of just a quick demonstration of what happens. It's a little bit difficult to parse, so you can take a look at the paper if you're interested. But the main idea is that the black line here, the solid line, is the exact sampler. So this is predictive resampling for like a super long time, like infinity basically. This dotted line is the truncated one. So I just stopped predictive resampling super early at like 30 data points or something, because let's say that was my computational budget. So you can see this dotted line very far from this solid black line, right? Like it's way too narrow. It doesn't seem to be, I mean, it's centered at the same place, but you know, the tails are way more narrow. And if you just add on this Gaussian noise, this carefully tuned Gaussian noise, you end up with this dashed line, which is hiding underneath the black line, that's almost kind of exactly the same. So instead of truncating at 20,000 or whatever, I've truncated basically 1,000 times earlier. But by leveraging this kind of asymptotic theory based on Gaussians, I get this crazy speed up, like a 10 to the 4 speed up with basically no real, like, I mean, it's a minor difference in the posterior distribution, but the approximation gets more and more accurate the later you truncate. So we can kind of take this approach further and actually do this with nonparametric methods as well. For example, with the quantile stuff, we managed to show that because your quantile function is a bit more unconstrained than the density, right? It just needs to be kind of monotonic and smooth. We managed to show that you can finish off predictive resampling, again with Gaussian noise, but in this case, it's a function. So we add these kind of Gaussian processes to our initial estimate. And it turns out that's a very accurate approximation. So on the left-hand side, you have the 95% credible intervals with samples. And on the right-hand side, you have the Gaussian process approximation. There's a very specific kind of kernel you need to construct, a little bit delicate, but once you get all of that right, you end up with basically a posterior that's indistinguishable visually. And then again, you get like 100 times speed up. So it's quite interesting because the kind of theory that you end up with is very different to that based on MCMC. Okay, so I'm now going to end with a conclusion, a little bit of discussion about what we talked about so far, and then finally a comment that I think is the biggest open question for this kind of methodology. And it's something that I've been thinking about very actively and would love to hear your feedback as well. So the predictive Bayesian approach, this kind of martingale posterior or predictive Bayes, is basically replacing the elicitation of your likelihood and prior with the predictive distribution directly. At least conceptually, that's what you do. And there are some cases where this really does offer some practical benefits. You can use this algorithm called predictive resampling. If you specify your model in a clever way where the updating is cheap, then actually it can be much more scalable to MCMC. It's not always the case that it's more scalable. Sometimes it's like kind of equally as slow, but at least some of the computational problems that you encounter are quite different. So you don't have to worry about convergence to a random object. Like in MCMC, you have to worry about the stationarity of your chain. Here, you don't need to worry about that. You actually just need to monitor the trajectories, which kind of converge to these fixed limits. Even though the limits are random, they do flatten out. You do need to do truncation, which was actually quite a big problem at the start, but a promising approach is actually to finish off predictive resampling using asymptotic theory. It's not really that different to using asymptotic theory in the frequentist case. Just instead of looking at like real populations, you're kind of looking at these simulated populations. The big question that I want to end with, which is a little bit of a downer, but I think it's also kind of an exciting opportunity, is that basically all of the settings so far that I've introduced have been the settings where data sets are IID. So quantile estimation, KDE, all the parametric examples. We've done some extensions to regression, but it's still pretty much IID. You depend very much on this notion that as you see more and more data, you know your parameter exactly. And that's a very kind of IID setup, right? Like you don't really get that for more complicated parameters. So it's a pretty big open question about what happens when we start looking at Bayesian models or settings with dependence. So I'm super interested in hierarchical models. I know they have broad applications in biostatistics, for example. So I'm looking at this with a student about how you would think about at least constructing predictive models that share some of the practical benefits of hierarchical modeling, things like pooling, for example. A more ambitious kind of approach is thinking about time series. There are some kind of openings here. You can kind of imagine that in time series, there are some parameters which are recoverable with infinite data. For example, the correlation for AR1 models. That's kind of the easiest example. So there are some kind of structure that's underlying this kind of time series. And actually, this is also quite closely related to these notions of parameters that I think was also the work of Phil David, where he spoke about these extrinsic and intrinsic parameters, like parameters that actually mean something that you can actually recover from infinite data, and parameters that just kind of index your model and don't really do very much, like kind of like a hyperparameter. And of course, if you want to get really ambitious, then you want more general dependent structure. Something like a network would be pretty crazy. But currently, it's not super clear. It seems like the way to actually approach dependence is to slowly relax kind of the independent setting, which is a little bit unsatisfying. And so when we wrote the original paper, this was also the biggest kind of criticism by Stefan Lauritsen. And it's still an open question, like whether or not we can solve this. But if we can, I'm hoping that there's some really strong practical advantages. Okay, so thank you very much for your time. That was my presentation. Here are some references just for the recording's sake, and I'd be happy to take any questions now.